So here's the plan. We will move on to chapter 4, which is graphing. We're going to skip the math models, and we're going to come back to the math models at the end. So the math models is basically, story problems, stuff like that. Is there a good way to learn axioms, or is the only way to memorize them? Well, so axioms, there's nothing to learn, right? Because axioms are the things that you claim are true from the beginning. So not all axioms are true. So what does it mean for an axiom to be true? Axioms are... So the way that mathematics works, including algebra, is that you define things, or you claim if these things are true. So those are the statements that you have at the beginning that you're just deciding are going to be true. And then from there, you go on to find out what are the consequences, or what are the things that follow from those initial truth statements. So for example, in geometry, there are 5 axioms in geometry that like you can draw a line between 2 points, that a point and a line will produce a circle, that alt-right angles are congruent, and there's one other one that I don't remember exactly what it was. Oh, that you can take a line segment and extend it indefinitely and it makes a straight line. And then the 5th one is called the parallel postulate, which is an axiom. So a postulate and an axiom are basically the same thing. They're the things that you claim are true, and then you find out from those truths which things, what else is true given these initial assumptions. So the parallel postulate is the one that says that if you have a line and a point that's not on the line, then there's exactly one other point that is parallel to the original line, or something where it's perpendicular here, and as a consequence of that perpendicularity, then these things never intersect. There's a bunch of different ways of formulating that are all equivalent. So the parallel postulate says basically that if you have a line and a point that's not on the line, you can draw there's only one line that is parallel to the initial one, in that they never intersect. However, if you ignore that postulate and you say, I'm going to say that this postulate is actually not true, what else can happen? Then you can get the different kinds of geometries where you can have, for example, on a sphere, parallel lines on a sphere look like this. They look like lines of longitude. And so here, 2 parallel lines actually intersect each other, and they intersect each other, I guess, infinitely many times. Depends on how you define the end of a line. But they intersect each other at the north and the south pole. But at the equator, their tangents are parallel to each other. So you can ignore the parallel postulate and come up with other types of geometries. If you assume the parallel postulate, then you get planar geometry. You get the geometry that we learned in 9th grade with, here's a square, and the area of a square is thus and so, and the ratio of the circumference of a circle to the radius of the circle is pi, like 2 days ago. However, if you assume that the parallel postulate does not hold, then you actually get different answers for the ratio of the circumference of a circle to the diameter of the circle. So for example, the circumference to the diameter. So for example, if we have a circle on a sphere, so here is a sphere, and you pick a point and you draw a radius of that point, then you get a curve that looks like this, right? The radius is going to be on a line of longitude that kind of goes all the way around. So here is my circle, and then you trace out from that what a circle is, which is the points that are all equidistant from a given point. So here's my given point, here's my radius, and now I trace out a circle like this. So that is the circle on a sphere, and it produces a shape that looks something like a cap. So a circle is going to produce something that looks like this, like the top of the Earth on the Arctic Circle. And here, the circumference is actually a lot smaller than 2 pi times the radius. So in fact, you can have a circle with a gigantic radius. You can have a circle with a gigantic radius that comes down here, and then your circle in the end is like that. It's tiny. And you can actually have the circumference of the circle be smaller than the radius of the circle. So, okay, let's imagine this. So here's the globe. We'll go from the North Pole. We'll say that North Pole is our thing, and the radius of our circle is going to be some line that comes all the way down like this, down to the Antarctic Circle. So here's the radius, and then you trace out the circle, and you're going to get something that looks like that, which is going to be the circumference of that will be the Antarctic Circle. And the circumference is going to be less than the radius in that case, which is kind of weird. So the relationship between the radius of a circle on a sphere and the circumference of the circle on a sphere depends upon the size of the sphere that you're talking about. So let's take a look at that just so that we can disabuse ourselves of all the things that we thought we knew. So what 2 pi r, so there's 2 pi r times the sine of theta, and theta is the angle from the pole to the radius. So there's a small circle on a sphere, looks like this, and it's 2 pi r sine theta. And so if you have, okay, so that's another way of doing it. That's not the way, 2 pi r sine theta. Anyways, there you go. Is the halting problem fake? I think the halting problem is real. What determines whether an axiom needs a proof like a theory? So an axiom, by definition, does not need a proof. An axiom is something that you assume is true and you prove everything else. There's no axioms, you can neither prove them as true or false. You just claim that they're true. That's the role that they play. So they're kind of like the fundamental aspects of your geometry or of your system. So it's similar to a definition. Like, we're going to define this thing and we're going to claim certain properties about it. So there's another one called like the Axiom of Choice, which is if you have an infinite number of sets, an uncountably infinite number of sets, is it possible to have a choice function that gives you one element out of each of those sets? And if you say that the axiom of choice is true, that if you have an uncountably infinite number of sets and then you can pick one element out of each of those sets, then you get certain consequences. And if that turns out, or if you claim that the axiom of choice is false, then you get other things that follow from that. So one of the really famous ones is called the Aktarsky Paradox. Aktarsky Paradox. So this is something that you can look up that basically comes down to, if you believe that the axiom of choice is true, then you have to deal with the Aktarsky Paradox, which is basically you take a sphere, you break it into pieces, and you get 4 spheres that are equal in size, or 3 spheres that are equal in size to the original sphere. So that's the Aktarsky Paradox. And so axioms play that role. You assume that they're true, and then whatever follows from that. It doesn't. Now, you may have issues about, do these axioms actually apply in the universe that we live in? And even that is a question about what do you mean by the universe that we live in. All right, let's see. What is next? Meant to go here. So let us move on to this section on graphing. And what does it actually mean to be graphing something in algebra? Blue points on a rectangular coordinate system. So in this case, the book is going to be talking about graphing on a plane. And so the book is going to be saying, all right, we have a plane. It's 2 number lines that look like yay. We have a number line like this and a number line like this. These are both real numbers. So you're going to have this one, and we have to define, okay, so this one is real numbers, and this one is also real numbers, and we have to define some way of arriving at a point on this plane. Now, this is a flat plane, so we're going to assume that the parallel postulate holds. And there are actually a variety of ways to arrive at getting to a point out here. So, for example, you could have a coordinate system where this number line is like this. So here's all of these integers, and then here are the integers on this real number line. And then you have an x coordinate and a y coordinate like that. So you say you move so far on this axis, and then you move so far on that axis. So this would give you a point x, y, and then you claim that this is the x-axis here. So you label this number line the x-axis, but you could call it whatever you wanted. It could be called the z-axis if you wanted. It's not. This is just a name that you assign. You, the user, assign this name, and it's a convention that many, many users agreed. Let's call this the x-axis, and we'll call this one the y-axis, and then we'll have a coordinate system that looks like this with x and y. And then if you have a 3-dimensional thing, which isn't covered in this book, but let's pretend that it was a 3-dimensional one, you'd have another axis that sticks out in a 3rd dimension, and it would have its integers like this, and this would also be the real numbers, and it would be the z-axis. So in that case you'd have ordered triples x, y, and z. So if you want to find a location on a plane in this coordinate system, you move so far on the x-axis, and then you move so far on the y-axis, and you end up with a point right here. But this is not the only way to map a point on a plane. So for example, if you have say you have a point and you want to tell someone else how to get to that point, there are a variety of ways to do this. you first of all, you have to define what your origin is. So for example, you could just define the origin as to whatever the location of the point is. So here's my origin, and the point is at the origin. So there you go. You don't have to move. However, in general, you want to have a generic origin that you get to choose. Maybe this isn't the point that you want to have at the origin. You want to have the origin centered on, I don't know, your home address or something like that. So in that case, you have your own origin set up, and then you have your point over here, and you need to describe how to get to this point. And another way to do it is to say just how far it is. So you just draw a line like this, and that gives you some distance. And that's a perfectly good coordinate system. In fact, what you could do is you could align your coordinate system along that line. So instead of having x go this direction and y go this direction, you could have x and y go like this. So this is the x direction here, and this is the y direction here, and then here's your point and here's your origin, and so it's just all along one line. Okay, but in 2 dimensions, in general, you want to be able to get to any point in the 2-dimensional plane, and so you need to have 2 coordinates. You cannot, if you want to have a 2-dimensional surface and make a map of a 2-dimensional surface, you have to have 2 coordinates. You can't do it with a single coordinate. Okay, another way of doing it would be to, like, here's your origin right here, and you have some point over here, and then you say, oh, you go out some distance like this, and then you rotate. Actually, I didn't do a very good job of that. So you'd go out some distance like this. It'd be about here. So here's the distance, and then you rotate this up by some angle. So that is your result. And so now you have a coordinate, which is the distance r. We'll call it the distance r because that's what the convention is. And then you have an angle here, theta. So you define the location of this point as r and theta. So again, you have 2 dimensions, one there and one here, in order to be able to map to any point on the plane. So here's your distance, and then the angle that you rotate. You have to choose an origin. Not only do you have to choose an origin for where the point where the origin is located, but you also have to choose a reference axis where your point can, from which you measure your other coordinate. So in the xy coordinate system, this is the Cartesian coordinate system. You choose that this axis is called the x direction and this axis is called the y direction. Okay, in this r theta coordinate system, you choose, and you choose your origin, and you're measuring relative to the origin in each of those coordinates. In the r theta, so like these circumpolar coordinates, you choose an origin and you choose a reference line. Okay, and so now a point up here has some distance like that, and then you choose an angle from the reference line. So it's slightly different than saying you have a single reference point. It's a reference point in both x and y, and they share that reference point. Here you have an origin and you have a line passing through the origin, and so you get one dimension or one direction that points the distance that you need to travel, and another one that points the angle that you need to travel. There's a slight difference between coordinates that are measured these different ways. So for example, in this direction, for the Cartesian coordinate system, your distances are, well, they have a unit of length associated with it. If this is a distance, then it has a unit of length associated with them. Or the way that you measure moving in a particular direction has the same units of whatever the axis is measured in. So this could be position and this could be time, like that could be time, or vice versa. But as you move from one point to another in this coordinate plane, you're traveling at some with the same units of that coordinate axis. Here, on the other hand, the angle doesn't have units. Okay, and notice that the angle that doesn't have units corresponds to a reference line rather than a reference point. And so the way that you would measure a distance here is related to, here's the reference line, and then you multiply by the angle to get a distance. But it's the difference being that angles don't have units, where distances do have units. Okay, now this is all assuming that this coordinate system that we care about so far, we've talked about, this is a spatial position, that you have some point in space, and you're measuring its position, and that these measurements have, or you're communicating its position, and these measurements have units of distance here and distance here, is typically the way that people think about it. But this is totally arbitrary, right? You don't have to have distance. It could be it could be voltage on this one, and it could be like intensity. So these could be two, in fact, it could be voltage, and this could be hair color. Hair color isn't something, like hue. Hue is a continuous thing. So you could have voltage and hue. So they're otherwise completely unrelated things, and you're just making a map to connect the hue of some object to the voltage that's applied to that object, for example. And so this is a way of mapping out, is there a relationship between hue and voltage? In that case, you're saying here's a number line, and this number line is a map between the properties of the real numbers. So you're choosing this to be a real number on this axis. So I want to make a map of the properties of the real numbers onto some physical world. So it might be a distance. In that case, you're mapping it like literally into physical space. It could be a voltage, it could be energy, which is a mathematical construct that you build based on your coordinate systems. By the way, this says energy, even though it doesn't look like it. And you're mapping this physical quantity onto a real number line. So the relationship between physics and mathematics is that mathematics is basically studying the properties of a number line, and physics is what happens when you take some physical property and map it onto the number line, and then use the properties of numbers in order to make statements about the physical world. So a way to describe what's going on here, like this hue, this would be a voltage hue. You call this a parameter space. So you have these two parameters, and it's the space of all combinations of voltage and hue. And then you would look to see, is there some curve that this thing follows or something like that. That's a little bit weird to imagine the fact that mathematics, they talk about abstract spaces. So there's no physical significance to the real number line. The physical significance comes when we try to map what we observe onto the real number line. So let's see, certain Pepsi commercials can affect color, so they do relate. Yes, that's probably true. All right, so another thing to consider about these coordinate systems that we're looking at. So we've already shown two different ways of mapping things. Another way to do that is you could have a coordinate system where the axes don't actually line up the same way. So you could have a coordinate system that looks like this, where you have one coordinate axis that looks like this and another coordinate axis that looks like that. And so if you have a point here, it's traveling along this direction and traveling along this direction. The difference here is that these angles are not 90 degrees. So like this angle is not 90 degrees. And so why do we not use these kinds of coordinate systems? We could. In fact, I'm pretty sure that there are places where such a coordinate system might make sense. Certainly in crystal lattices, it makes sense to have coordinate systems that look like this. So for example, if you stack a bunch of oranges up, excuse me, suppose you stack up a bunch of oranges, you're going to get piles that look like this. Oh, that was bad. Let me go back. Let me try to do this more betterer. Make me proud. There we go. So you're going to get a structure that looks like that. And notice that in this case, the oranges, they don't make squares. They make little trapezoids or rhombuses like this. Okay, so you get a hexagonal pattern. So here's the hexagon, and the hexagon is made out of these different trapezoids. And so you can, in this case, if you want to say, oh, here's my orange, the origin of my orange stack, and I want to measure the position of some other orange in the stack, then you could measure along some direction like this, but you don't measure up because you miss oranges when you measure up. You would measure, your second axis would be tilted relative to the vertical, so that you're moving directly from one orange center to the next and from one orange center to the next in the two different directions that these oranges are being stacked or laid on the ground or something like that. So this is called hexagonal close packing, and it's an example of a coordinate system where the two coordinate axes are not perpendicular to each other. There's streets. Let's see, that's the wrong computer. Let's try this computer. Streets in Seattle. So if I go to maps, and we come, oh, actually I can do it here in Las Vegas. I don't have to go to Seattle. So here in downtown Las Vegas, in this area, notice that there are different, like the streets don't come in at the same angle. So moving south along Las Vegas Boulevard through the downtown area actually moves you both in the east-west direction and in the north-south direction at the same time. It doesn't move you only in one or only in another. So Las Vegas Boulevard is inclined like this, and so if you move some coordinate down Las Vegas Boulevard, you're actually moving both east and west and north and south, as opposed to Maryland Parkway, which runs right here and eventually runs straight to the university. Maryland Parkway runs directly north and south, and so you're only moving in one. So you have this external coordinate system, which is centered on the Earth, with the North Pole being north and the South Pole being south. So here's this external one. And now you have the street that is a separate coordinate system that is laid on top of that. In some cases, the streets might coincide with the directions from the globe, and in other cases, they may not. And you can have cities that are laid out so that both of them, you could map, if you were to continue Maryland Parkway due north, where would it intersect on this other coordinate system that has a different angle of orientation with it. So these kinds of things are important. Why do we have these coordinate systems? Why do we use the coordinate systems that we use? So one question that you might ask is, why is it useful? It seems like it should be more useful to have a coordinate system such as the one that we're most familiar with, where this is actually a right angle. Okay, why do we have this x-axis in the horizontal direction and the y-axis is always or almost always in the vertical direction? At least when we first picture it, it's in the vertical direction. And the answer to that is that the advantage you get when these two things are perpendicular to each other is that motion in one direction is independent of motion in the other direction. So when they're perpendicular to each other, the motion along one line is independent of motion along the other line, which means that if I have an xy coordinate like this, I can change the x-coordinate and keep the y-coordinate the same, or I can change the y-coordinate and keep the x-coordinate the same. Where if you have a coordinate system where the angle is not 90 degrees, where they're not perpendicular to each other, like this, then if I change the x-coordinate, I'm changing the y-coordinate as well. And if I'm changing the y-coordinate, then I'm also changing the x-coordinate. So this type of coordinate system no longer has the property that these two coordinate designations are independent of each other. So this is called an orthogonal or orthogonal basis. It's an orthogonal coordinate system, which means that the two axes are perpendicular to each other. So orthogonal is a fancy way of saying perpendicular. It's a multi-dimensional way of saying perpendicular. Perpendicular is technically in just 2 dimensions. And if you have a 3-dimensional coordinate system, then you want something that's orthogonal. Excuse me, but this is not the only trait that these things have. You could imagine a coordinate system where, for example, you have one axis that looks like this. That's the spacing of, you're mapping it onto something, and that's the spacing that you use. And the other axis has a spacing that looks like this. Okay, so a place where this might happen would be, for example, distance and time. That time moves in, and that's the spacing that you have there, and distance is the spacing that you have here. And so these two lengths aren't equal to each other. The length between your map on the real number line for the distance coordinate is different than the map or the length that you map to the real number line in the time coordinate. So while these two dimensions are orthogonal to each other, you have this orthogonal basis, they're not the same size. So in that case, the way that you described it is you say that they're not normalized. So they have different lengths corresponding to the unit. So if you want to normalize them so that they have the same length in one direction as they have in another direction, then that's called an orthonormal basis, orthonormal. So ortho meaning that it's orthogonal, and normal meaning that the distances have all been stretched or squeezed appropriately so that the same distance on one number line corresponds to the same distance on another number line. So that is some of the things about, like, when you're making a graph, which is what this chapter is about, making graphs. When you're making a graph, let me adjust this momentarily. What it means to put something on the coordinate system, what the coordinate system represents, those are all kind of things to consider. So in the case of what we're talking about here, we're just saying here is a real number line and here is another real number line. And we're going to look at what are the properties of things where you map one set of real numbers onto a different set of real numbers. And that's going to be some kind of curve. So this curve is a way of connecting numbers, one set of real numbers to a different set of real numbers. So that at this location of the real number, you get this value for a different real number. And there are certain types of properties that this map can have. For example, you could have a curve that looks like this, where you're mapping the entire real number line onto only part of the real number line. So you're taking the whole real numbers and you're mapping it onto only a portion of the real numbers afterwards, right? So if we have, here's our coordinate system, we have all the real numbers in this direction, we have all the real numbers in this direction, but then our map that we make that connects these two real number lines together only looks like this. Then we're mapping the entirety of the real number line onto only this portion of the real number line. And in that case, you can't go backwards. You can only go backwards if the function that you're mapping one real number line to the other real number line it's called bijective. It means that it's one-to-one, that you only have one value. So a single value on one real number line corresponds to only a single value on the other real number line. And that, so bijective is, it's one-to-one and onto. One-to-one, so you could, onto means not only does one input value give you only one single output value, but every input value gives you an output value. An example of a function that is not one-to-one and onto would be something that looked like this. So you get all of the, or something that looks like this, for example. So like the exponential curve. Let me redraw this. So you could have a curve that looks like this. Okay, so this is an exponential curve, which we'll get to probably later. But this takes all real numbers as an input. Actually, this does have an inverse function, doesn't it? I'll have to look up that definition to make sure that I know what I'm talking about. But it only maps to this half of the real numbers. I think, okay, so I'm still confident that this is not a bijection. We'll take a look at that and make sure that my definitions are right. So it takes the entire real number in, but only half of the real numbers as the output. So it's only positive numbers that are output, but you can have positive or negative numbers as the input. So in this case, you can have a whole range of the real numbers that are undefined. If you take the inverse function, you get a whole range of numbers that you can't plug in because it doesn't give you there's no value of this function that is negative. And so if you take the inverse, there's no way to put in a negative value and get a real number of the back out. So let me briefly take a look at that and make sure that I know what I'm talking about. So a bijection is a one-to-one correspondence or invertible function, the function between the elements of two sets where each element of one set is paired with exactly one element of the other set, and each element of the other set is paired to exactly one element of the original set. Is one-to-one, injective, and onto surjective. I don't remember what these words mean. I used them along like 20-something years ago. Mapping set onto set Y. The term one-to-one correspondence must not be confused with a one-to-one function. Okay, so these are all the differences between these things. A bijection set X onto set Y has an inverse function from Y to X. If X and Y are infinite sets, then the existence of a bijection means they have the same number of elements. For infinite sets, the picture is more complicated. Concept of cardinal number. Okay, so this says that you don't have to map to all. This makes me think that this exponential curve is actually a bijection. It's one set maps onto, like one complete set maps onto another complete set that's the same, has the same number of elements. And the fact that there's negative numbers, like there's a restriction on the domain or the range of this function doesn't affect whether it's a bijection or not. Okay, anyway, so there are these mathematical terms that are important for making the graphs, or like what does it mean to graph something? So I would recommend looking up bijection. on your own time to hash out some of the details. The important thing for our purposes is that we have these number lines. It's the real numbers here, real numbers here. We choose them so that they are orthonormal. We choose them so that the spacing between these elements here and these elements here are the same. So the unit length in this direction and the unit length in that direction are the same. And we choose them to be orthonormal so that if you move or you have a coordinate in one direction, its motion or its position is independent of the position in the opposite direction or in the corresponding direction. And this way you get ordered pairs, x, y. What does it mean if these things are orthonormal? What it means is if you have some coordinate or some position here and you want to add to it another coordinate pair. So let's say that you have this one, which is going to be at 1, 2, 3, 4. It's going to be like at 4, 4. So this first point is 4, 4. That's this one. And I want to add to it some other point like 2, 1. That would be this one. How do you add these things together? Well, the way that you add them together, so this point here is 2, 1, is that you start with the x-coordinate and you move 2 more in the x-coordinate, in the x direction. And then you start with the y direction and you add 1 more in the y direction. So that means that you just add this element and this one together, and that gets you 6. And then you add this one and this one together, and that gets you 5. So adding these 2 points together means that you just add each coordinate separately from the other. So you have an ordered pair, x, y, or another way to put it, if you have a, b as an ordered pair, plus C, D as an ordered pair, then you're going to get A plus B and C plus D as the result. Okay. Now, one of the things that happens when you're adding ordered pairs together like this is that, in general, a lot of the properties of addition are preserved. So we talked before about the fact that you have these properties of addition, that it's associative, it's commutative, that there's an identity element, there's an inverse element. So for example, if I have AB, it has an inverse element. That inverse element is minus A minus B. And when you add these things together, following the rules that I described, you're going to get 0, 0. And this is the identity element. So the additive identity element looks like this. So this is, these also form a group, like addition on ordered pairs forms a group similar to addition on other things. This is not always going to be true. There are other ways of doing, oh yeah, right. How about if I do that correctly? This is A plus C, and this is B plus D. Very good. Thank you for pointing that out. Okay, so slight correction there. A plus C, B plus D. So you add this one and this one together, and you add this one and this one together, and that gets you these two. That's the result. And it has inverses. It's got an identity element, right? A, B plus 0, 0 gets you back A, B, which is exactly what we have with regular addition. This is not the only way of adding ordered pairs together. You can come up with other ways of adding ordered pairs that is different than this, but that still has the same properties. So for example, if I have A, B, and I wanted to add C, D, yeah, that's right, I can get a different result than what I described. In this case, you do not have an orthonormal basis that you're talking about, and this is a different kind of addition. This kind of addition is going to be, all right, wish me luck on this, BD over here, and then this is going to be A, D plus BC. Okay, so this kind of addition also has inverses and has an identity element, but and so the identity element in this case is going to be C equals 0 is an identity element. So A, B plus 0, D is going to give me what? If I follow the same formula, then I'm going to get that's equal to AD plus 0. And then over here, it's going to be BD. And then you have a rule that says, okay, this is equivalent to AB. You have a mechanism for saying that this thing is equivalent to that thing. So this is what happens when you add fractions together. So if you add fractions together, you've got AB plus CD. And the way that you add fractions together is you find the common denominator. So the common denominator is BD, and you multiply the top and the bottom by what's missing from the side. So you'd multiply the top and bottom here by D, and then multiply the top and bottom here by B, and you get AD plus BC. Okay, and that's basically what I said right here, AD plus BC, and then here's your denominator. So this is another way of adding things. It has inverses, it's got the identity element, and it has a way of simplifying the result. So that if you have 2/4 in the end, that this also simplifies to 1/2. You say that these two things are equal to each other. It's the same. You claim that it's the same point. In fact, it's slightly different because it's written differently, but then you have simplification rules that can get you from here to there. So adding things together is, well, there are a variety of ways of adding pairs of numbers together that still preserve the interesting properties that we want in the real number line. So for the cases that we're looking at in this chapter, we're looking at, here's a graph, and these are real numbers, and these are real numbers, and we have the addition rule that A, B plus C, D gives you A plus C and B plus D, like that. And that's just taking a point. Here's your origin. You define a point, this coordinate, you have another point that has a slightly different set of coordinates, and when you add them together, you basically add in the x direction, and you add in the y direction independently, and you get the result in the end. All right, here is a question. A black hole, oh yeah, so one of the things about general relativity is you're looking at space-time, which in other words, so when astronomers or physicists measure the positions of things in space, they are using space-time. So they're using space-time, and in that case they're saying, all right, we are going to map physical positions onto a coordinate system. That coordinate system is going to be defined by the path that light would take traveling between those locations. So in particular, what they're going to say is, here are a bunch of regularly spaced locations like this, and I'm going to connect the path that light takes as it goes between each of these locations. Okay, so here's the path that light would take. If I shine a flashlight, it's going to do this, and then they're going to have the same thing in the y direction is going to go like this, and then so they have something that looks like that. But everywhere along this path that light takes, it might distort because of the presence of gravity. Light is affected by mass. The path that light takes is affected by the presence of mass. And so you define your coordinate system based upon, you say light defines what a straight line is, and now you have to come up with some way of mapping the curved path that a light beam takes to a rectangular path of an orthonormal coordinate system with real numbers. So here is your orthonormal coordinate system. It looks like that. You notice that the path that light takes is curved relative to that, and so you have to come up with the map between the curved path that the light takes and your chosen Cartesian coordinate system that is a bunch of orthogonal real number lines. And so that map between the curved path that light takes, which is the physical path, and the mathematical path that you describe here, which is this social construct of I want everything to be orthonormal, is called the metric. So the metric tells you, as you're moving along some mathematical path that is pure and straight and doesn't deviate at all, to the physical universe where light actually bends around the presence of some massive object, the metric tells you how to make that map. So that's general relativity kind of in a nutshell. Let's see. GR has a whole system for describing coordinate handling. Yeah, so that's kind of what I described. I had a teacher always say they make mistakes. Who's paying attention? Yeah. Is a number pair different from a vector in this case? Okay, so in this case, there are things called vector spaces that physicists use all the time. And in mathematics, a vector, okay, so computer science can have maybe has a different meaning to this, but if you have positions here and position here, and then you're constructing something, x, y, you can say, okay, here's this thing, and I'm going to claim that this is a vector. That displacement is a vector. Vector. In mathematics, a vector is not just a set of ordered pairs. So if you have time and space, like t and x, that can also form a vector. But you can have other things that don't that don't form a vector. So unfortunately, it seems as though this is a circular argument. A vector is something that transforms like a vector. The way that it's typically said is a tensor is something that transforms like a tensor. Basically, what that means is I'm going to come up with a transformation rule. I'm going to come up with a rule where I say, if I can take this and I can do some transformation to it, and I'm going to get this other thing, and certain properties that this thing has are maintained in that transformation over here. So I take a vector and I do some transformation to it, and I get a result out that maintains certain specific properties. Then anything that satisfies that continuity of properties is a vector. So when someone says a vector is something that transforms like a vector, if you just take a series of numbers and you plug it into, you just take a series of numbers and you plug it into this transformation, this function here, and you start with something that looks like that and you end with something that looks like this, so that whatever these properties are that you began with turn into a deviation from those properties, then you would say, okay, this series of numbers is not a vector. So a vector is something where when you put it into these kinds of transformations, there are certain aspects of what you put in, certain properties that are defined up front that you put in, that are preserved when it comes back out the other side. So in order for something to be a vector, it has to satisfy this kind of transformation. And then this thing is defined. I don't know, is it like a linear transformation is going to preserve angles and something. So that's what. So simply having a coordinate system does not necessarily mean that you have a vector space. Do you have a practical example of a use of a null space? I would have to have a deeper understanding of what it means to be a null space then. Is the null space the things that all map to the origin? I'm sure there is a practical example. Let me take a look real quick. What is the null space? Null space. Kernel of a linear map is a linear subspace of domain map which is mapped to the zero vector. Okay, so it's all the things that are mapped to the origin. Is there a practical example of the use of a null space? If you're doing a projection, so if you have, suppose you have a stick. So here is the surface of the Earth. Okay, and pretend that these are right angles. So this is actually a right angle. It's just laying on the surface of the Earth. And you have a stick that looks like this, sticking out of the ground. When the sun is overhead, that stick is going to cast a shadow, right? So you have this stick that's sticking in some direction. The stick is sticking, get that? And when the sun moves over, the shadow is going to be cast in different places. But then you could have, the null space would be all of the coordinates in this. The sun can be any position in the sky, or maybe it's the light, that's theater lighting or something like that. The light can shine from any position in space, but there is a line in the physical universe that we live in where the shadow will be cast at the foot, like it will be in its own shadow. The stick sticking up out of the ground, it will be in its own shadow. And so that would be an example of the null space would be all the points along this line where this function that takes the projection of the stick onto the ground maps to, I guess in this case, the origin would have to be there. But that would be an example. All right, let's continue moving along with what we're talking about. We haven't even gotten to the point where so we plotted some numbers on the number line, but we haven't seen how to map these things, or like what it actually implies. Okay, so one of the things that the book shows, I remember that this book is coming from the OpenStax Elementary Algebra from the OpenStax library. I'm going to zoom in so that I don't have to draw this figure. Okay, so this is showing the quadrants. So when you have two real number lines that intersect in something like this, it's going to divide the plane into 4 pieces. Those pieces are called quadrants, and they're related to the origin. And then you can just look at the number line and see, okay, so these numbers are positive and the up is positive. That's also convention to have positive going to the right and positive going up. If you flipped over the y-axis so that positive was going down, it doesn't necessarily change the properties of the real line. It would just change, does it even change what you mean by these coordinates or like by these quadrants? I don't know. So can I think of an example of where I want a coordinate system where the positive numbers go down? Yes, that's actually pretty easy to come up with an example where you would want your coordinate system to be upside down from what you learned in your math class. So in math class, you learn positive goes to the right and positive goes up. In physics class, you might be like, okay, I'm going to start at some height. Here's my thing. I'm going to drop a ball. So here's me leaning over to this cliff, and I'm going to drop this ball, and I want to find out how far it's traveled, some distance here. And if when I initially drop it, it's traveled no distance, so that's going to be 0. And if I just want to measure how far has it gone, then that means that distance grows. Positive distance is downwards. Okay, and that's just, so I'm defining in this case a coordinate system where that is the orientation of the axes. So, and in fact, honestly, in this case, if you're dropping it straight down, you wouldn't even have this one. You would just say x is down. Okay, but if you did have both directions, say you threw it to the side, then you'd have x is to the right and y is down. So there are a variety of reasons why mathematics is, I think, being a little bit overly restrictive in how it orients its coordinate axes. But Australian mathematics is definitely upside down, and the angle is measured counterclockwise, at least when viewed from our point of view. Okay, so so this coordinate system that it's describing here with positive to the right and positive us, or positive being up, that's a convention. It's a convention that's useful, but it doesn't necessarily need to be this way. And so these statements about the quadrants are useful, just recognizing that, if I was in a physics class and I had positive going down and to the right, would I still call this the first coordinate? If I was making a map of stuff, I probably still would call this the first quadrant. No, I didn't say that right. The first quadrant. So even if I had this going to the right and this going down, I would probably still call this quadrant 1 and this one quadrant 2. So that's interesting. I hadn't ever wondered that question before. Okay, so these 4 quadrants, at some point they're going to be useful. Not totally sure when, but we can pretend. Okay, so you're plotting points, negative x, positive x, negative y, positive y. It's going to put you in different parts of the plane. Whenever you have a plane and if you have a plane and you put one line through it, you're going to get 2 halves. When you have a plane and you put 2 lines through it, you're going to get quadrants. One thing that's actually interesting to note is that there's a thing called projective geometry. So projective geometry is geometry that happens when you're looking at something from the side. So for example, if you take a circle, here's a circle, and you tilt that circle to the side, you're going to get an ellipse. And so there are a number of things like properties of a circle. For example, if you take 2 points that are opposite each other on the circle, then it will go through the geometric center. So you take 2 points that are opposite each other on a circle, it will go through the geometric center. The same thing is true with an ellipse. If you take 2 points that are opposite each other on an ellipse and connect it with a line, it will go through the geometric center. And that's a consequence of projective geometry. So if I take a circle and then I just rotate it, the circle turns into an ellipse, and you're continuously deforming all of these lines, at least how it's projected into your eyeball. And so there are certain properties that are preserved when you go through that projection. The same thing is true with coordinate systems. You can take an orthonormal coordinate system and you can tilt it, like rotate it to the side, and produce a coordinate system that looks like it's crooked. Okay, and it's because now you're rotating it in a higher dimension that you're taking something that's orthonormal and you're making it not orthonormal anymore by rotating it in a higher dimension, but then observing it again in back in 2 dimensions. So that's kind of weird. All right, so these coordinate systems, that's good enough for that. Having these points is a map from, basically tells you how to get to a point in this space. The fact that this is a 2-dimensional space is, perhaps it's not all that interesting, but in if you want to use mathematics as a description of the physical world, which is not necessarily the purpose of mathematics, but it's certainly a useful application of mathematics. Computers do things that aren't necessarily in the physical world either. It's just a series of numbers. But one of the reasons that we might want to learn mathematics is because if we map the physical world onto a mathematical space like this, a mathematical plane, and we have a coordinate that describes all the possible positions in that mathematical plane, then we might be able to come up with a physical model where we can describe how something acts in, like how something is moving through the universe or interacting with things in the universe, and put it onto this mathematical model, and then use our understanding of mathematics to glean insight into what's going on in nature. So, time and space is probably one of the most common maps that you make in mathematics, in physics, that is kind of an abstract space. It's one thing when your dimensions are all the same, when your two axes are the same, that one is a spatial dimension, like they're both spatial dimensions, so this is like horizontal and this is vertical. It's another thing if one of them has completely different units, time and space. So can you ever create 3D coordinates? Yeah, so 3D coordinates work exactly the same way, in that in a 3D space, you just have, these are all right angles, and then you have, in this case, this would typically be x coming out this way, y here, and z goes up. And there's a convention that when you're doing a 3D space, that if you rotate clockwise, rotate counterclockwise from the x to the y axis, then you're rotating about the positive z axis. So basically, if you curl your fingers in the direction that you're rotating from the x to the y axis, then the z axis is the direction that your thumb points with the right-hand rule. That's the convention. It doesn't have to be this way, but that's the convention that everyone has adopted, is the right-hand rule. So we don't care about left-handed people. We only care about right-handed people. And you curl your fingers in the direction of the rotation from x to y, and your thumb points in z. Is how you do that. 5D coordinates is, so 3 blue, 1 brown has a number of things about how to visualize things in higher dimensions, but that's kind of how that works. All right, so back to this. Now we want to, the next part of this chapter is going to be looking at how do you, what does it mean to actually plot a relationship between points on one of these graphs. So not just individual points, but now collections of points. So in that case, what you want to come up with is there a way that you can take, here's your coordinate system, is there a way that you can take the x values of the coordinate system and map them onto the y values? What does it look like to take an x value and have it correspond to a y value? In this case, there are a lot of ways to do that, but what you want to have is some constraint on the values of x and y. So if you have just x and y as coordinates, x can take on any value between negative infinity and positive infinity, right? And y can do the same. So the whole plane is all of this stuff. All of this stuff is the whole plane. Anything between negative infinity and positive infinity for either x or y is allowed. So there's no constraint on this. But if you place a constraint on the relationship that you're looking for, then you're no longer allowed to be anywhere in the whole plane. Instead, you're constrained to live on whatever set of points satisfies the constraint. So you could, for example, say, I want all the set of points, but I want to constrain the y value to be equal to 5. In that case, what happens? So if you constrain the y value to be equal to 5, x can be anything, and so x is unconstrained. Notice that there's no constraint on x, there's only a constraint on y. And if you go up like this to y value equal to 5, then you're going to get something that looks like that. So x is unconstrained and y is constrained. If you wanted to constrain the x value, I want to constrain x equal to 0, then that's going to mean that y is unconstrained, and I'm going to be living on the y-axis where x is equal to 0. So in general, when we're doing like graphing lines, what we're doing is we're saying, I want to constrain both x and y. So instead of just constraining one or the other, I'm going to constrain some combination of x and y equals, one of these is an x plus y is equal to something like this. Okay, or I'm going to say some combination of x and y is going to be constrained. So I'll have like ax plus by equals c. So here is a constraint. Initially I could have any possible value for x and y that I want, but now I'm going to say I only want the values of x and y that make this thing true. Okay, so if I only want the values of x and y that make that thing true, then I'm going to end up with some line that slices through this space. It actually reduces a two-dimensional space down to a one-dimensional space. It reduces the two-dimensional plane down to a one-dimensional line, and that's going to be important. So that is what we're going to be going on to in the coming weeks is what does it mean to map, well, the coming weeks, like next week, what does it mean to map something to satisfy these constraints? Like what do these constraints do? How do we show the constraints that we get from, like what are different ways of representing what this line is? What are the different ways of writing down an equivalent line, and how can those different things be useful?